Hello and welcome. Today we'll consider question 4, which states, for which pairs of sets A, B is the symmetric difference of A with B equals the union of A with B? For which pairs of sets is the symmetric difference of A with B equals the intersection of A with B? And for which pairs of sets is the symmetric difference of A with B equal to just the set A? Take a couple seconds to try this out for yourself, then you'll get some hints, then we'll proceed with the proof. Alright, for some hints, first step is to try out some casework, try out some example sets A and B, and just consider what the symmetric difference of them is. And in particular, for doing that, you should recall, or go back and check what the symmetric difference of two sets is. Alright, let us begin. So to start, we'll note that the symmetric difference can also be written equivalently as the union of two sets subtracted against the intersection of those two sets. What this means is that we can easily answer question A by just saying for any sets where their intersection is the null set. That is, for any two disjoint sets, their symmetric difference will be the null set. However, additionally, this lends insight into the rest of the questions, in the sense that the symmetric difference is all those elements that are not in both sets at once. So, if it's all those elements that are not in both sets at once, there is no sets for which A symmetric difference with B is equal to A intersect B, except for the trivial case. That is, the trivial case being if A is the null set and B is the null set, then we see the A symmetric difference with B is going to be the null set union the null set, which is the null set, subtracted the null set, which we know to be the null set. This trivial case is a nice exception that we should recall the empty set often satisfies. Therefore, we see the only pair of sets for which this is true is the empty set. Finally, for the last part, note for which pairs of sets A symmetric difference B is equal to A. Well, that is all the elements that are in A or B but not both. But if we want this to just be the elements in A, that means the set B has to have no elements, and in particular has to have no elements in common with A. That means B is the empty set. That is, any pair of sets A and B where B is the empty set will have the symmetric difference of A with B is the empty set. And we can see that by our definition that this works, since we have that A unioned with empty set is just A, symmetric subtracted against just the empty set, because A intersect the empty set is the empty set. Therefore, this works, and to confirm that this is all of them, we'll see that if A is any non-empty set, then A union B will have some elements besides, if they're disjoint, then B will have some elements besides A, so A union B will be not just A, and so when you subtract off the intersection, you'll have some elements that are not in A. But if B is non-empty and B has some elements in common with A, then A union B will include at most A. However, you will always be subtracting off the elements in common, so you'll not get all of A. Therefore, B is limited to just the empty set. And with that, we're done. Thank you for watching.